4K and 8K. Just when we thought in our earlier lives standard def was good enough with NTSC, then we went to standard def digital, cleaned things up a little bit, and then moved to the world. Can somebody adjust the lights again? I think it looks better the other way. And now 4K and 8K. I think it's a very fascinating topic. Some people say it's never going to happen. Some people say it's happening. Some people say it's going to happen in certain aspects of our business and not others. I'm sure everybody has their own opinion, but what I see is an acquisition world. Why not? 4K, 8K, sky's the limit. If you can figure out a way to handle it and capture it and store it for archiving purposes, for acquisition, all the better. Getting it to somebody's home in 8K, I don't think that's going to happen too soon. It'd be nice, but is there a business reason to do it? Well, in Japan, their economy is based on things like this. They have a lot of mandates to move in this direction, so they're doing it. In North America, is there a business case to do it? Can anybody tell the difference? If I have 4K or 8K in my home, there's some people say, you're not going to be able to see the difference. Some people say, oh, I can tell the difference. But is there a market reason to do it? How do you get it from point A to point B? In my travels, see what you think, but I deal with people that do the outside broadcast. They do the big trucks and all that stuff that go around all over the place doing sporting events and special events. 4K, they're doing, for sporting events, they have a 4K camera. And what they can do, take the 4K right to a disk array, a big box like this with hard drives in it, and they pull off the instant replays. That way, within 4K, they can zoom a 1080i picture within that. And that's all they're doing. They said 4K never leaves the box. There is no 4K distribution. There's no 4K glue from end to end to move this stuff. 8K, no better. So the thing of it is, you acquire it at the highest possible quality you can, and then you do with it what you need to do it from there. It's pretty much how I see it. As business cases change, as technology gets cheaper, as people get, I mean, everybody has a screen 3 times as big in their house, then there's a market reason to do all that. Motivation for 4K conversion. Well, film is expensive, it's slow, it's inflexible. It's a manual process for assembling the shows. You have to send it somewhere. It's got to be mailed. It's got to be tracked. It's a physical, tangible thing. And you have to print all these. You have to control, make sure they don't get stolen, make sure they get there when they're supposed to be there, and make sure they leave when they're supposed to leave there. So it's a very manual, expensive process. I was at a Hollywood Post Alliance back in February. An interesting point that was brought out. The world has 100 and some years of experience of archiving film. Nothing new there. We can put it somewhere and we know it's going to be okay for a lot longer than I need to worry about it. Video on a file, you can't just put somewhere and forget about it. Every 3 to 5 years, somebody's got to say, now what do I do with it? And this could go on for eternity. I work with the Library of Congress outside of Washington, D.C. Their mission is to archive the assets of the United States of America as far as audio and video for the life of the Republic plus 4,000 years. Well, how do you do that on a hard drive? I suggested granite tablets, you know, punching 1s and 0s into granite, but they didn't think that was funny. But that might last, I don't know, about 4,000 years, but it's a challenge. Another thing that's not, I don't think, really being thought of, at least I think it's going to be overlooked as long as possible, it's the archiving. Also, the cutting room floor. When you have film, you know what you use and what you don't use, and you make another reel of the stuff that you don't use. Digital, what am I going to do with the stuff that I don't use? Well, let's kind of just forget about it, and nobody has to worry about it. That needs to be archived, too. Can't just put it in a reel and put it in the refrigerator in a cold storage somewhere, and it's going to be there. Because the problem with the digital world, you're dealing in abstractions. This is a tape. I know where it is. I know what machine it goes into. I can write on it. I can hand it off to somebody. I can mail it to somebody. I know where it is in the library. Digital, The world we're going to, 4K is part of that. It's for archiving high quality something. Hopefully it has a long life and multi-purpose distribution is part of the business case. 4K formats, market drivers, cost-effective technology for theaters. You can satellite, downlink a movie, you can mail a hard drive, whatever you want to do somewhere. But usually it's a satellite, it's encrypted, so that way they have it when they need it, and it's more controlled that way. High-end viewers. My first VOD project at IBM, I was all excited about. MPEG-1 and then MPEG-2 over ATM networks. This is exciting stuff. And I was at a meeting getting all excited about it, and the lead marketing person said, "Not so fast, young man. No one cares how it's delivered. If you could get video to somebody's home with 2 tin cans with a string in between, the customer would be delighted. It does not matter the technology behind it. It's all about content, the quality of the experience." Well, we have larger picture formats, rich color, bit resolution, higher refresh rate. Some people are saying we're moving in the wrong direction, 4K, 8K. We should be going in the same direction but with frame rates. The higher the frame rate, the less motion artifacting you have, the cleaner the picture. Our eyes are happy with it. Some people saying forget this 4K, 8K, let's just go to higher frame rates, higher refresh rates. Higher bit rates, you have more flexibility for production and post-production, which is really, in the acquisition side, creating the content, what it's all about. You want to have the highest resolution to the product, whatever your delivery mechanism is. You want to optimize the facility that you're using for transmission, because transmission is what usually costs the money. The content is one thing, but actually getting it to someone is another major expense in this whole business case. Well, why 4K? We have higher resolutions. We'll talk about that. Frame rates, extended color, XYZ color spaces, lookup tables. Trying to digitally emulate film. Some people say, well, the higher we go in resolution, you're actually ruining the entire film look. Because film has a look. Maybe you've noticed it, maybe you haven't. You look at a good old-fashioned movie compared to a home video you shot with your cell phone or a camcorder, it doesn't look the same. Some people say film, all the problems of film is actually how we see the world. When I'm looking at you towards the front of the room, everybody in the back of the room is out of focus. That's the way the world really is. It's where a brain works. I center on a part of the room and everything else is kind of soft. Film is very good at doing that. You can control your depth of field. You can use different speed of film. It's a well-known technology. We've had 100 years of figuring this out. And that's the look some people say we're not going to get with film. It's too sharp. It looks too much unlike the real world. Film is more real world. Obviously, that's an artistic debate, but I see the point. Sometimes I see an old-time movie on a brand new high-quality display. It doesn't have the same look. It just doesn't look the same to me. Image sizes. What size? Back in the good old days, we had good old-fashioned NTSC. Now, how big do you want to go? How small do you want to go? It's a delivery mechanism. You start out with something big, and you can always lose your quality and size as you go. What you do not want to do is start with 720 and go up to 4K. You could do it. Would it look all that great? Probably not. But by downscaling, you're usually going to look pretty darn good no matter what you do. It's easy to lose. It's hard to create something from something that never existed. 4K, well, there's two different sizes. For television people, you take 1920 by 1080 times 4, you come up with 3840 by 1160. You take a 2K film production and you end up with the 4096 2160. So television people are usually talking about 4K in the 3840 domain because it fits more into the world of television. Because what we're doing in the acquisition side, quite often, is 4 SDI 1080i pipes, 4 BNC connectors. And I was at a facility and they had a nice new Sony, not even released to the market yet, beta version of the Sony F55 camera. And I was dying to try this. We hook up 4 SDI connections, go to our waveform monitor, we go to a nice display they have there, and I disconnected one of the SDI connections and I said, I want to see what happens here. Nothing happened. A quarter of the screen goes black without any drama, no twitching. I go, let's hook it back up and see what happens. Nothing happens. All of a sudden, the quarter of the picture that I disconnected just appears back there seamlessly. There's no weird things happening. It totally surprised me, but that's where we are with the technology. You can pick any of these. There's 4 wires if you're doing 4 SDI connections, because this doesn't fit in the one SDI connection without going to higher bit rates than we want to deal with at this point. So right now, the infrastructure that exists in most facilities can handle 1.5 gigabits per second or 3 gigabits per second, so that's fine. You get 4K, we're definitely the much higher bit rates. But television people, here's the way we're going. Digital cinema, you have extra space here, which is not really how we think in television. 1080i is pretty much where we're going. The chroma, the space, is the 709 color space. And you can see by the legend, that's the yellow. I guess that's how it's showing up on the display here. That's the color space. Is it everything under the rainbow? No, it's not. Is it pleasing to the eye? I hope so. That's the direction they're going. Because once again, your brain is not really as sensitive to color as we think. You start getting out here, this green compared to that green, it's green. So why worry about it? But once again, the bigger the color space, we're doing XYZ color space, that's all the way out here, beyond the human vision model, because you want to start with more, you're going to end up with less. Data rates. It was bad enough with standard def SDI of 270 megabits, going to 1.5 gigabits per second. Dual link, you take 2 1.5 gigabits and put them on separate cables. So we're going from a serial technology to a parallel serial technology, where we start going to 4K. We do 4 HD SDIs. So we're back into the parallel domain with 4 serial connections. So once again, serial is nice, everything fits into one wire. As soon as you go into the parallel domain, even if it is serial, you still have velocity issues between your connections. You want to have matched cable types, different velocities on different cable types. You want to make sure that the length is the same. You don't want one to be 10 feet and the other one to be 30 feet long. That would definitely probably cause a problem. I don't know for sure how tolerant the spec is, but there's some issues there. You start falling apart. It's not putting the elements where they belong at the right time. So with the different data rates, the challenge we have, the laws of physics unfortunately apply to television. It's kind of shocking and disappointing, but it does. Cabling is a great low-pass filter. It would love to pass DC and heat up like a toaster element and glow in the dark and all that stuff. It'd love to do that. What it doesn't like to do is to pass high frequency, because a lot of the world is a low-pass filter in many ways. When you go outside on a beautiful morning or a beautiful evening, you see a sunrise or a sunset. Is the sunset blue? No, it's red, because the low-frequency light makes it through all the atmosphere, because as you're going towards the horizon, you're going through more air, and that attenuates the high frequency, so the sunrise and sunset look red. Any Navy people, sonar people in the room? Well, in case you never noticed, never been on a submarine, I spent a little time on one with IBM doing video productions. That was interesting. Submarines do not have windshields. They can't see where they're going. And when you look at a map of the world from a submarine person, it's looking down from the North Pole. They see the northern hemisphere, or they see the southern hemisphere. That's how they think of the world, because they spend all their time going between the oceans under the polar ice cap. Surface ships can't do that. Submarines, it's a great place to go to hide. Nobody's up there to mess around with them. So when you're doing that, how do you avoid hitting an iceberg? Like the Titanic had trouble doing. Well, submarines could do it all the time because they're always under icebergs. That's where they go. So how do you avoid an iceberg? Hollywood always has that pinging sound. That's a bunch of baloney. That's Hollywood. How sonar works on submarines is like bird chirps. Very like chirp, chirp, chirp. Very high frequency, even higher than I can go here today. The reason is it has high resolution, but it doesn't go that far because the ocean attenuates high frequencies. When whales communicate, it's low, like a lion roar, an elephant trumpet, low frequency, travels far, and that establishes your domain. Birds chirp so they can find each other. Other animals make noise to find territory. So with that said, the sonar puts out these chirps. They can see it's an iceberg, go left, right, down, and go around it. If they would put out low frequency sound, they'd be giving out their location to everybody in the northern hemisphere, which is not the whole purpose of what they're doing. So high frequency attenuates quickly. You go outside, busy street, somebody drives by with their car stereo turned up loud. What do you hear? You hear the low frequency, not the high frequency. So the laws of physics unfortunately apply to television. We're going to talk about physical layer here next section, and we'll talk about the limitations. So anyway, just trying to set the stage for the challenges we're getting into by going to 4 SDI. If you go to 4 SDI, that's 1.5 gig times 4 different connections. Well, we need to go to RGB color space. Fast progressive. It's not going to fit in 1.5. We need to go to a 3 gig. So we end up with 4 3 gig pipes. So the laws of physics, again, are being challenged because coax really isn't interested in passing these frequencies. It'll do it if you're nice, but it would rather pass NTSC at 4.2 megahertz all day like the good old days, and they would be perfectly happy with that. How do we multiplex? How do we structure all this stuff? Our friend, start of active video, end of active video, we're trying to show here. We have start of active video, it's kind of hard to see. We have our 3FF, our zeros, which we didn't get into. You have XYZ word, I oversimplified it. You have all ones, all zeros, all zeros. Then you have an XYZ word, which defines what line is it, what line number. That all needs to be determined. So you connect up a BNC connection, it knows where it is in the scan. It says this is line 215 or whatever it is, and it knows where line 215 is. It locks, and you're in business. Optional ancillary data is what we're talking about in the previous section, where you put in the stuff, the closed captioning, the embedded audio, AFD, all that good stuff goes in here. End of active video, that's after the end of active video. We still have other information to say where you are in the end of active video. So the point is, we can have different infrastructures, but essentially it's an evolution of SDI. 6 gigabit was shown at NAB. Our friends up there, you can see who's doing that. It's not standardized. Some people say, let's worry about 4K before we go to 6, and some people are saying, well, we have enough trouble with 3 gigabits per second, so now we're going to 6 gigabits, which challenges cable. So eventually, you have to go to optical. You're at the physical limit of what copper can handle because it's not designed for high frequency RF. Because when you do a 3 gig signal, point I need to make, we'll make it even stronger in the next section. When I put a 3 gigabit per second signal into a piece of copper coax, you need a third order harmonic to get a square wave to go through it. So you're asking that coax to pass a 9 gigahertz signal to get a 3 gigabit per second signal through it. Good luck with that, because the square waves and all the issues we'll talk about in the next section. So here we are, 6 gig, well, 10 gig, let's just go optical and get it over with. Because optical, you can do a lot more than 10 gig if you really want to. The copper doesn't care, it's a piece of glass. So anything we're going to do to it, it can pretty much handle. But optical interfaces are the way the world appears to be going, but then some people say, well, we'll just go IP and not worry about all this optical stuff. Well, I think we'll get the optical first. IP, just too expensive to move uncompressed video, but that's Carl's opinion. Okay, so quad link, 1.5 gig, what can you put in it? For your reference, this is all the different formats. Because remember the good old days of NTSC. Then we had 525 and 625 standard def SDI. Now we go to these links. What color space are we talking about? YCVCR, that is color averaged. RGB is not color averaged. So essentially how you want to start looking at this, we talk about compression, we get into this I think a little bit. 422 is color averaged. What does this mean? In my own little brain I say pick 4 pixels, any 4 pixels horizontally. Each of the 4 pixels gets a luma sample. 4 pixels, 4 luma samples. The 2.2 is color average. So out of 4 pixels horizontally, I skip a pixel for color samples. So I do sample here, skip this pixel, do a sample here, skip that pixel, and keep doing that. So you're sub-sampling the color. That's how we get into color difference, YCVCR, which is color averaging going on. Why? Because on the transmit side, you can't just skip pixels, you do color averaging between pixels. And the human brain is not sensitive to color edge detail. We really don't have any color edge detail. The detail we see in our everyday lives is in the grayscale. You're looking at a white slide here. You have a white background with black text. That's not a coincidence. You're taking notes. White piece of paper, dark ink. Fine print. High contrast is how we see fine print. If this was a dark green background with dark gray or black text, you'd have trouble seeing the finer print. So that proves right there you have less color resolution than you do shades of gray. So with that said, I start going into RGB, alpha channel. That means it's full. Every pixel gets a sample. I'm not half sampling anything because it's RGB. There is no luma. Luma is derived by full RGB, I have white. No RGB, I have black. Full red, no green, no blue, you have red. So RGB, there is no averaging going on because that's what makes it RGB. So you can see here, you can do 10-bit, 10-bit, or 12-bit. 12-bit, you're definitely out of the broadcast world. You're into digital cinema, archiving, acquisition of spy satellite stuff, whatever you're doing. Alpha channel, forgot to mention this. This is for compositing. When you're pasting layers of video together, the alpha channel is where you cut the hole in the picture. Like chroma keying, the green screen, the blue screen, that's the alpha channel. This color here doesn't exist, so I put something in the hole that I cut. That's alpha channel. XYZ 12-bit, you're definitely in the digital cinema because this is where you're doing 2K digital cinema, which means XYZ, you have beyond the color space that we see, but a computer graphics system needs that because you lose every time you do a special effect. So you end up with high quality color of what the human brain actually sees. And just to make it even more exciting, point to make, I don't think it's in this presentation, one of the things that's slid out over time. Standard def, it's SMPTE 352. SMPTE 352 does not exist in standard def digital. It's optional in high def SDI digital. It's required, you start going into your more exotic formats of multiple links or 3 gig. SMPTE 352 tells the receiver, here's what I'm sending you, and here's what you need to do with the ones and zeros I'm sending you. Is it color averaged? Is it XYZ? Is it RGB? Because receivers kind of would like some help to say, you're sending me all this stuff, just tell me what I need to do with it, okay? Now I know what to do with it. SMPTE 352M. If you start having conflicts, you're putting in, especially get to this level here, start putting stuff in and the receiver doesn't understand what you're doing. It says error, unlocked or something. You look at the SMPTE 352 test that we have in our test equipment or some other device you have and see if it's valid. It might be cranking out one thing, but SMPTE 352 says it's something else, and you have a receiver sitting there going, I don't have a clue what to do with all this stuff. I'm dealing with 4 links of HD SDI, 1.5 gigabits, and now I don't know what's luma, what's chroma, what's color average, what's not color average. It's kind of a long story. SMPTE 352M, I should put this back in this presentation. That's where it would go. 4K formatting. A 4K image, how do you do sub-images? Because you're multiplexing it. You have to get 4 feeds somehow. Well, there's different ways of transmitting it. There's discrete 4 channels, or you can start getting into interleaving, which always blows my mind. And here we are, quad link. As I said before, you pull link number 4, that part of the picture goes away. It's a simple method, which the Sony F35 beta release, not available until Christmas. I saw it as one distributor. They let me play with it under the threat of death. They say, whatever you do, don't have the power off when you put the BNCs on, have the power off when you take them off. Be careful with the lens. This connector right here is kind of shaky. It breaks off real easy. It's like, whoa, this is not ready for production. But anyway, it was fun to play around with it. Used in post-production and camera application. 4 links coming out of a camera, it makes sense. It's good for your post-production work. You're moving around, you're storing. Everything is discrete on 4 individual BNC connectors. Requires large memory to store images because it's got to buffer all the stuff for one. It can't produce a picture because it adds some latency. When you start saying, I got to produce this line of this picture to make this line of that picture, so to put this all together requires some delay. You're buffering. You say, you wait over here in this buffer, you wait over here in this buffer, until I get over here, then I'll call you out and put it all together. So in the world of acquisition, this is acceptable. You do not want to do 4 link like this for distribution. You want to do interleaving because you're taking pixels from each of the 4 links sequentially. So you're building the picture as you go, pulling information out from each of the links. So for transmission and encoding, here's what you're going to see. I can't see how anything can possibly go wrong with that, but it's more complex. But latency, less processing delays. You're not buffering entire pictures before you display something. You're pulling it out and creating it as you go. Less memory configuration. You're not buffering as much. For your reference, this gets a little deep, but you're showing how you can put it into 2 10 gig SDI links, just in case you're so inclined. What about 8K? I don't know what about it. I was at Hollywood Post Alliance in February, and people were saying, you're not going to be able to tell. Unless you have a huge screen, the average human being at the viewing distance you have here is not going to be able to tell the difference. You go up and stand with your nose against the screen, you're going to see the difference. But is the consumer doing that? Probably not. Acquisition, 8K, 16K, whatever you want to pay for, go for it. But as far as how do you move this stuff around? You put it to a hard drive, then what do you do with it? You got to transcode it right away. Then you're in the business. I have 8K, I can't move it anywhere. I have to make a file out of it. Have to compress it. Well, are you going to have 8K resolution after you do the compression algorithm? Or did you totally blow the whole concept of doing high resolution video to begin with? Because it's only as good as the transcode that you're doing to it. So you have different sizes, 7K, 8K. For your reference, just showing you how the multiplexing is going on with your link A and B, how this all hopefully gets put back together on the other side. Interleaving looks complicated to me, but it's supposedly, as I said before, less memory, less buffering, less latency, and you're pulling stuff off pixel by pixel from the various streams as it's needed. Okay, so the physical layer, I believe, is next. Okay, yeah. Why is not what I opened? Video interfaces. Back in the good old days of NTSC, it was easy. Going through a piece of coax. We have poor little coax here. Back in the good old days of 4.2 megahertz, life was easy. 4.2 megahertz of sine waves. Haha, sine waves are easy. Now we're putting in square waves. Square waves and physical copper really don't get along because 270 megabits for standard def, 1.485 or 1.5 gig for high def, 3 gig, 3 billion ones and zeros per second for 1080p and above. Problem is, This is a low-pass filter. What happens? It is my rise and my fall time. This is the entire challenge. This is an eye pattern. Let's start with that. Here's an eye looking at you. There's another eye looking at you. It's like the eyes in this conference room. And I got to commend you people. I don't know how you do it, but the eyes are staying open. If the eyes are open, I'm the transmitter, you're the receiver. The information is transferring. If the eyes start to close, well, it's thinking about the weekend, next summer, you know, getting your new tires for your car, making sure the snow tires are on in time, all that stuff. This is time, this is amplitude. 800 millivolts. It's not much. Why couldn't we do 5 volts? Not even 1 volt we're dealing with here. It's how stingy. So anyway, 800 millivolts plus or minus 10%. This is time. This is a unit interval. And we'll talk about how that increases with standard def, HD, 3 gig. Time and voltage. It's a typical representation you would see on an oscilloscope. Voltage and time. The challenge is the rise and the fall time. If I would extrapolate, let's say this is a 3 gig signal. I come up here for this transition, I go up here, I come back down, go down here, come back up, and do my cycles there. It takes 9 gigahertz, if that would turn that into a continuous sine wave, because this rise and fall time takes 9 gigahertz of frequency response. That's a whole big difference from 4.2 megahertz, 9 gig. You're way into the RF frequency. So what happens? Cabling being a low-pass filter, I lose the high frequency. That's the square of the square wave. I lose high frequency, I start getting a rounded off sine wave. That's like a bicycle sprocket. You're riding your bicycle, you start filing down all the teeth. Eventually, things start to slip. You don't have enough bite. It's not enough determination. Is it a high? Is it a low? And when do I make that decision? As things start to round off, get lower amplitude, video equipment that's confused says it's nap time. When things are fixed, you wake me up and I'll get back to work. So there is the challenge. It's the rise and the fall time. How do I get overshoot? That's too much high frequency. Because what happens in the physical domain, you have a reclocking distribution amplifier. Oh, I've got them all over the place. I'll never have physical layer problems. You get what you pay for. It's an electronic device. Reclocking distribution amplifiers, the first thing it does, well, what it does, if I have a crummy signal coming in, it wants to get it back to 800 millivolts, so it does that. If my high frequency is gone, it tries to put back in the high frequency. It tries to square up the square wave that degraded into a sine wave. When you're listening to audio, you don't have enough high frequency, you equalize by adding more high frequency. You can overdo it. Reclocking distribution amplifiers that are doing equalization can actually add too much high frequency. So you have overshoot, ringing, and all this stuff. If it's too extreme, your decision points start getting corrupted, so the receiver doesn't know when is it a high, when is it a low, and when is even a unit interval. I don't know. Reclocking distribution amplifiers reclock, so any jitter, which is frequency instability, gets fixed. So they amplify, equalize, and stabilize. How good is that being done? Well, the more you pay, usually stability costs money, cheap is cheap. Do you know that? Once again, test equipment. You put in a known good signal, distribution amplifier, see what comes out, because that is what you're propagating into your entire system. Once again, you don't see it with your eyes, you don't hear it with your ears until it's too late. You can have a device that's putting out a crummy, unstable signal, and the picture, sound seems perfect. You're removed from the physical layer. So an eye pattern is how you actually see what's happening at the electrical layer. So once again, time, voltage. How do I get timing issues? Well, let's go back. How do I get rise and fall issues? Well, high-pass filter, a low-pass filter of coax, the more I have, the more filtering is going on of your high frequency. So a cable that's twice as long has less high frequency coming out the other end. That's a problem. So I have high frequency roll-off, my square wave degrades, just because of the physical characteristics. Okay, what if I have... A wise person once told me, cabling does not get angry, it gets even. Everything you do to it, it remembers. So when you're speccing cable, get the right cable for the job, get the right strippers, the right terminators, and then from the moment you pull it off the reel, you're nice to it until you retire. Because everything you do to it is pretty much permanent damage to that cable. I work with people who do big events, you know, Formula One, golf matches, all that kind of stuff. And they have people walking over their cables, they have golf carts running over their cables, and things start falling apart. I was at one facility, just hanging out and helping out, and they said, why is this feed constantly coming and going? They told, hey, go out there and walk the cable over to the other end of the parking lot and see what's happening between the two trucks. And the guy on the radio says, there's a whole bunch of police on horseback standing on our cable. Well, tell them to move. No, you come out and you tell the police to move. They'll get bored, they'll go find something else to do, and eventually they moved on, and now they have their cable. It's like, we better replace that cable. It's not designed for, you know, 6 horses standing on it for 10 minutes. It's permanent damage. So what they do, either throw it out, or they cut it in half and they make it shorter. So they're constantly ending up until they have cables this long, and they used to be, you know, 100 meters. Constantly cutting it in half. Well, eventually, so be nice to it. This cable, if I bend it like this, or like that, or step on it, it is changed. This is a flexible waveguide. For any RF engineers in the room, when you have a transmitter, you have hollow pipes that move the content, the electrical energy, from here to the transmitter, to the antenna. So every time you impact, this is like, if I would step on this, it's the same analogy of stepping on a garden hose. I step on a water hose, less water comes out the other end. That's obvious. But the problem is I'm pulsing ones and zeros at 1.5 gig, 3 billion times per second. And those pulses hit the restriction where I'm stepping on the garden hose and actually reflect the pulses back from where they came from. You have a reflected wave. You have a forward-moving 3 gig square wave. Hits the restriction because a change in termination. You're trying to have 75 ohms from one point to the other. If I step on it, that's not 75 ohms anymore. That's a change in termination. So I have a reflection of energy back to the source, which means the forward-moving wave is now less and the shape of it's distorted because they're colliding as they're traveling. Also, by having a reflection, you're increasing the heat load on your circuit that's putting the signal out in the first place. And heat is never a friend of electronics. So energy going out, reflecting back, well, it's not doing anybody any good on the other end. So with that said, be nice to your cable. Don't over-tighten wire ties. That changes the impedance. Don't put it in the back of a rack and slam the door and fold it over. Don't tie it in a knot. Or my favorite, you're trying to make everything nice and groomed in the back of your rack. Oh, you're 3 inches too short here. Nobody's looking. Stretch it. Oh, look at that. I do beautiful work. With NTSC, who cares? 3 gig? I wouldn't bother doing that. But yeah, it does happen. You over-tighten the wire ties. Somebody said they had trouble between point A and point B, and they had a nice interval of wire ties. Too tight because it looked nice and groomed. Cut the wire ties, the signal comes back. Like, we shouldn't do that anymore. So, eye pattern is your physical layer. I love it. I'm an engineer. It's cool, but I think it's overused. I'll show you where it's correct to use it and where I would say you're missing the point. Your rise and fall between your 20 and 80%, my 20 and 80%, that's where we're actually doing your measurement. Jitter, we'll talk more about that. Alignment jitter, got some good slides on that. What is jitter? Jitter is frequency instability. This is a fingerprint of the jitter. If this was twitching around here, that would be jitter. It's frequency instability. It's like a bicycle chain that's too loose. It's flopping around. There's a limit to that. Once again, interoperability. The signal can be dancing all over the place. The receiver says, oh, I can keep up with that, no problem. And it says, I'm done. I can't keep up with it anymore. It's finished. Like a bicycle chain falls off, it's too loose. What causes jitter? Well, we can't blame the coax on this one. You could, but really what it's about, it's in the active domain. If I have a source going to a destination, if the source is unstable, well, the signal coming out of it is unstable. Cheap is unstable, expensive is usually more stable. I have deviation. I have 1.5, I have 3 gigabits, and it's wobbling back and forth. Frequency modulation, phase noise, whatever term you like to use. But unfortunately, that taxes the receiver. It's like two people dancing. Well, they can choreograph nicely. One person goes crazy, the other person says, oh, I can't keep up with you, and that's the end of it. It's the same thing in the electrical domain. Jitter is frequency instability. What causes it? A piece of garbage to begin with. You bought cheap stuff, and it doesn't get any better with time. Time also makes it worse. As equipment ages, it becomes perhaps less stable. If heat, everybody's putting more and more equipment into a rack because it's smaller and rack space is expensive. Real estate by the square foot costs money. So you put more and more equipment in a rack because it makes sense. Heat goes up. Heat is instability. So is your equipment room being cooled properly? Your rack's being cooled properly? Is the cooling fan in the device working? Is the cooling fan in the device clogged with cat hair? All these things cause instability. Also aging equipment. As it goes down the road, it gets bumped around. You can also have, what we're showing here is the frequency of instability. This is an eye pattern that is beat. In our test equipment, we have highly stable circuits. That's what you're paying for. The clock coming in from the outside world and the clock internal to our device. It's looking for a difference. If the clock is nice and stable, you have a flat line. If there's instability in what's coming in, you start to see a fingerprint, a signature of the instability. You run through different filters. 10 hertz all the way up to, what do we have here? 100 kilohertz filter. So this is saying high pass filter of 10 hertz. Above 10 hertz, I have instability. Above 100 kilohertz, I have no instability. This is how you make friends when you're complaining about somebody's DA or somebody's routing, whatever, not being very stable. They'll say, well, tell me what this filter says, what that filter says. And okay, at 10 hertz, I see this signature here. This could be a square wave, a triangle wave, a sawtooth, random. And that tells the circuit designer what the stability issue is, the fingerprint for identifying the circuit instability. Take a picture with your cell phone, email, and they'll go, well, let me see, that might be the whole list. Could be a switching power supply failure. Could be a cold solder joint. It could be ground loops you have in your facility. It could be you have your coax running over a 480 three-phase transformer. Get it leaking into your system and causing instability. This is the fingerprint. The person on the phone will say, thank you very much. I have an intelligent person calling me. This is a wonderful day. Because this is what they need. This is what they live by when they're designing the stuff. So if you have stuff that's out of spec, speaking of spec, green is good, yellow is marginal, red is out of spec. So you can see, how do you, like anything else, how do you want to see it? You want to see an eye pattern, jitter, because jitter is always determined on the filter you're using. So Tektronix uses all the SMPTE standard filters to see eye and jitter. This is more of a graphical, text-based, pass-fail, bar graph type of an approach. If you don't want to look at this, this, and this tells you pretty much the same thing for the less enlightened, or just take a picture of it and it tells somebody what's going on, your filter, your cable loss. You put in the type of cable you're using, 1694 or whatever, and that way it gives you a display specifically for testing the quality of 1694. You can see your cable loss, approximate cable length. You put in 1694 by looking at the quality of the eye pattern, it will say there's approximately 1 meter or 100 meters or whatever of cable by the how the high frequency is attenuated at the physical layer our equipment extrapolates, because maybe you don't know. Between here and the other room, is it 2 meters or is it 100 meters? Between here and there, I don't know. But it might be what's causing my problem, just a long cable run. So jitter is frequency and stability. So back to the eye pattern, we have a long cable run. I lose amplitude, decrease in frequency response. I have my eye opening narrows. Do you see an eye pattern there? Been with groups? Oh yeah, I see an eye pattern. No, you don't. You see an eye pattern, but I wouldn't say you see a great eye pattern. Termination issues. You have the ringing and the overshooting. Here it's just long cable runs. And here, unequal rise and fall time, which is usually an electronic issue. It's inside the box causing the problem. Jitter measurements. I think we touched on this. For SD, HD, and 3 gig, you have timing jitter. This is a SMPTE spec. In our units, you put it in the SMPTE timing jitter mode for 10 hertz and above, and it gives you all the attributes for that. Alignment jitter is the variation of clock signal. You're extracting the clock. Thing to remember, in parallel communications, you can have RGB, HV, sync, and all that kind of stuff. You can have separate clocks galore because you have a separate wire for each of those. In serial communications, you're putting everything through one piece of wire. Unless we go to 4K, then we have multiple wires. But you have the clock is derived from the signal itself. There's no external clock. The highs and the lows and the transitions determine your clock. And here is the 10 hertz and above, 10 hertz and above. This is 100 kilohertz and above, 100 kilohertz and above. So you see different frequencies, gives you different signatures, and the people doing your troubleshooting can look at all this stuff and say, here's what I think we need to do. We had a bad production run on that circuit board, it's scrap, whatever they need to tell you. Check the cooling fans. Another part that got cut out of this seminar, I went to this whole SDI structuring. Thing to remember, SDI, whether it's SD or 3 gig, is non-return to zero inverted with a scrambling algorithm. Non-return to zero doesn't return to zero between clock pulses. Inverted means there is no polarity sensitivity. Because typically in the world of logic, we think of a high as a 1, a low as a 0. In this, a transition is a high. No transition between clock pulses is a logic 0. That simplifies circuit design because you're not worried as you're flipping through gates. Do I maintain polarity? Is a 1 now a 0? If there's a change, it's a 1. If there's no change, it's a 0. Before I forget to mention that, some people are getting creative because not too many people are doing standard def SDI anymore. So that equipment is kind of on the shelf collecting dust. Somebody gets the brainy idea. 270 megabits per second. That is the same as MPEG DVB ASI. So I can use my standard def routers and my glue to move MPEG around my facility. Wow, I'm a local hero. We have all the stuff we're not using. Now I have a new life to getting MPEG moved around in my facility. The danger is ASI is polarity sensitive. A high is a 1, a low is a 0. So if I'm going through SDI circuitry, it doesn't preserve polarity, it might not work on the other side. It's coming in, it's not working. I was working with, was it Verizon? They, like most cable companies, they take feeds in from local community. Oh, give it to me ASI. Okay, great. Well, I'm sending it to you, I don't see anything. Somebody said, well, go up to your router, what connection do you have it on? It's on port number 1. Okay, move it to port number 2 and see what happens. Oh, look at that, it works. Because some devices, odd and even ports, some are polarity sensitive, some of them aren't. So it's by moving to one different connection, all of a sudden their ASI is making it out to the cable company. Polarity sensitivity is not a given in devices. SDI doesn't care. ASI, you got to have a high as a 1, a low as a 0. So with that said, there's also a scrambling algorithm in SDI. This is a pathological stressing signal. Let me make that point. What it's doing is something you shouldn't be doing to serial digital video. Serial digital video has a scrambling algorithm, won't get into that, but what it does, you can put the lens cap on, you don't have all zeros. You zoom in on the sun, it's not all ones. Because in serial communications, you need constant transitions, like a bicycle chain. Highs and lows, regardless of the content. This breaks that scrambling algorithm. What we have here, the magenta is 1 high, 19 lows, 1 high, 19 lows. 20 highs is down here, 20 highs, 20 lows, 20 highs, 20 lows. This is like filing off 19 teeth on your bicycle sprocket and leaving 1 tooth. You're stressing it. If it's going to stay locked, then you're doing pretty good. If the chain is loose a little bit, with only 1 tooth out of 20, the chain's going to fall off. It's the same way with serial digital video. Tektronix developed this 20 years ago. It's patented but never protected, a gift to the world of electronics. How you can stress a serial connection. Checksum. This is what we're looking at before is a matrix. Well, here's actually what this is all about. You're looking for maximum DC content. Because what you're trying to do is 19 highs, 1 low state. So what you're doing is you're stressing your SDI content. You have a repeated shade of magenta, which is stressing it, perhaps breaking it. And here we have, oh, let me point I didn't make. This is stressing the equalizer, which is putting the highs back into the rounded off, squaring up the square wave. This is seeing how well that's happening. Phase lock loop, this is the clock. You can see a noise sweeping through my PowerPoint, isn't that neat? And what you see here, you have your long strings of 20 highs, 20 lows, 20 highs, 20 lows. That's checking, that's stressing the clock. The moral of the story is, if I put the matrix as a test signal into my system, I go to the test signal generator, put SDI checksum in there, and I run it through my facility. If I see it on the other end, you've not fallen off the cliff. If I put this in and I see nothing on the other end, something in your chain was living on the physical layer, right on the edge of the cliff, hanging on by its fingernails. Picture was good, sound was good. I put this in and it pushes it over the cliff. Now is the time to figure that out, not wait till it actually falls over the cliff. So with that said, color bars looks good, live video looks good. I put this signal in and I see this dull, not exciting looking test signal. On the other end, I was not living on the edge of the cliff. Color bars looks good, live video looks good. I put this in, I see nothing. You were right at the edge of the cliff. Maybe you didn't know it, but this forces you off the cliff to say you were living right on the edge. If I see this, what you want to do is go to the longest run of cable in your facility and add, 10 meters, 20 meters. Keep adding cable until this goes away. That way you know your margin. Document it. What I said about baselining your patient, if you have this and it looks good, you add 20 meters of cable, and then it goes away, you add 30, you say, well, 20 it could handle, 30 it couldn't. You come back in 6 months or 6 years, it might fall off the cliff with 10 meters of cable you just added. Because people do things to cable. They drop raised floors on it, they have horses standing on it, they do things to it when you're not looking. Cable does not improve with age, like your car. Every abuse you do to your car, someday it might cost. If you own it long enough, something will break. It's the same thing with a facility like this. You abuse it, you get closer to the digital cliff. Enough said. As I said, eye patterns are great. I think they're cool. I can look at them all day. They're overused. If I'm running around a racetrack for an F1 event and I see people looking at eye patterns, I go, nah, 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 nah. Eye patterns are designed, keep using this cable here, an eye pattern, pick that up later, eye patterns are for looking at a signal on this much cable. An eye pattern is for looking at the signal integrity of a device at the end of a short cable. Not on 100 feet of cable or 100 meters of cable. It's overused. Because when you find a problem, then you do an eye pattern check on a short piece of cable and say, this distribution amp is no good. This routing switcher is no good. This device is no good on a short piece of cable. If the eye pattern's out, there's something wrong in this box. Looking at it on the first turn of a racetrack is not the right way to do it. This is what I recommend. And people say, I wish I knew about that years ago. So hopefully this sinks in. This is the video session screen. Like our intensive care ward screen, this tells you all the stuff that's going on. What you can do is see what feed you're coming in, 720p, 1080i, whatever. Start of active video placement. If I have a problem there, I have a serious problem. Line length, line number, field length. If something is wrong here, I have serious interoperability problems. But the problem is, it might work on this display here, but I'm sending a signal out that has these fatal or nearly fatal errors. It might not work anywhere else. Everybody's saying, I don't get it. Stuck bits. For luma and chroma, you have a 10-bit signal, the bits should always be changing. If I'm before an encoder, my least significant bits are here. This is the small changes in shades and colors. I want a 10-bit signal and an 8-bit signal. If I'm coming off of a decoder, down from a downlink or whatever, I will be looking at most likely an 8-bit signal. What you're seeing at home is an 8-bit signal. Why? Because you can't tell the difference. Are you doing blue screen and green screen at your house? If you are, it's going to look pretty bad. Does the broadcaster care if it looks bad? No, they don't. So why send you bits you don't need? They need 10 bits for blue screen, green screen, and special effects. 8 bits, you're having a wonderful time watching TV at home. So 8 bits is what you should see after a satellite or after an encode, 10 bits before. If you have stuck bits, it's an L or an H. It says they're stuck low or high and they're not changing. So your small changes in shade and color aren't happening. So you go from 1024 color space like a 256 color space. That's what you're seeing at home. Gamut. Let's talk about, how am I doing with time? See how deep I want to get into this. 1:30. Gotta keep moving. We're doing all right though. Okay, so what we're doing here, my status screens. Green is good, red is bad. That's just the convention that we use. Errored seconds, errored fields, percent of errored fields. What's an errored second? 1 second of time that has 1 error or maybe 1,000 errors. It's a unit of measure the human brain can comprehend. Can I comprehend microseconds? No. Can I comprehend a second? Yes. So it's 1 second of time that has errored information. Why do I care? When you're running a facility for luma, chroma, RGB errors, or gamut errors, you want your errored seconds to be close to 0, errored fields close to 0, percent close to 0. This gives you an idea of how clean your facility is from the color and luma creative color space. That's fine. The real topic I want to drill down deeper into is CRC errors and checksum errors. CRC for luma samples, CRC for chroma samples. Status OK, errored seconds, errored fields, percent of errored fields. What does a CRC mean? CRC is active video, checksum is ancillary data. The ones and zeros that I'm putting in, okay, I'm going across this line of video here. As I'm going across this line here, I'm doing 2 calculations. A CRC for luma samples and a CRC for color samples. And I get to the end of the line. I do a magic rocket science calculation. I come up with a CRC, cyclical redundancy check or code, for that line of video. I get to across here, I'm doing 2 calculations on each line for luma and chroma of all the luma and chroma values, pixels. I come to here, do a magic calculation, I throw that into the serial stream, that travels with that line of video. And I do the same thing on every single line. Here's the beauty of it. If my eye pattern is falling apart to the point of not being decodable, or I have hits, I have vagueness as a high or a low, or no high or no low, I start getting errored seconds. If you hit the reset button, it goes back to 0. In 24 hours, a super clean facility will have errored seconds 5 or less. You know, cosmic rays leaking in or whatever. It just happens. What you don't want to see, you send somebody out to the first turn of the racetrack between the two production trucks or whatever, and they have errored seconds every second. Video looks good, sound is good, but it's telling you you're on the edge of the cliff. Because every second of time has corrupted ones and zeros. You can't see it, you can't hear it, you can't smell it. But it's telling you what I'm putting in at the source, point I didn't make. Our device does the same calculation on the same line of video. If the CRC inserted at the source does not equal what's calculated at the destination, you're having hits. Your ones and zeros are becoming confused. Important. If I have 1 errored second every second, you're on the edge of the cliff. You might not know it, but you just told yourself you do. If I have an errored second every 10 seconds, not so good. Errored second every minute, I've seen worse. The more errored seconds you have, the more you need to be saying, what's causing this? Do I need to go to fiber? Do I need to, where the cops were standing on the coax with horses, we'll replace that section. Do I have ground loops between trucks? Something is going on. Look at the CRCs and see what's happening. It tells you, are your ones and zeros making it? Checksum. This is the ancillary data. To the left and to the top of the picture. These are those packets with the, all zeros, all ones, for the SD, the DID and the SDID for the closed captioning, embedded audio, AFD, and all that good stuff. This is telling me, are those packets being received in the same quality they were sent? This is put at the source, destination does a recalculation. If that value equals, congratulations, all the ones and zeros made it. They survive. If they don't equal, you have errored seconds, errored fields, percent of errored fields is telling you you're moving towards the edge of the cliff. New formats for your enjoyment. Always look down here for 444, XYZ 12-bit. You're into the digital cinema range. For multiplexing, for talking about 3 gig, there's different ways of mapping into a 3 gig infrastructure. There's A and B level. Let's get to that. A level, native 3 gig. Okay, so what? Well, because the B level is multiplexed. 2 HDSDI connections in one 3 gig, because 1.5 gig, 1.5 gig fits nicely into a 3 gig infrastructure. Because dual link was the earlier days of 2K and all that stuff. I said, why does anybody care about dual link and 3 gig? Why would I put 2 HD SDIs on the one piece of coax? Then 3D came along and gave me the answer. That's how people were doing it. You can put left eye and right eye, 1080i for example, into one piece of cable which fills up a 3 gig cable. Because left eye and right eye timing is everything between what you see in 3D. Anybody doing 3D? Anybody glad they're not doing 3D? It's amazing. Every time I hear about a new problem, it's like, wow. Without getting too deep into it, 3D makes a whole lot of sense in acquisition Hollywood because they can fake it in post, they can do all kinds of stuff. Delivering it to the home, I can tell you about my friends at ESPN, what they think about it. They had a $12 million truck they had contracted that's now doing HD work and no 3D. It's like, it ain't happening because it costs too much money. Too much money. Is anybody paying more for advertising for 3D? No. Does it cost more? Yes. That's usually not a good business case. It's costing me 6 times more, but I can't charge a penny more for advertising. Is that a business I want to stay in? No. It's a business you want to run away from. So anyway, multiplexing 2 HD SDIs into one 3 gig, just for your colorful enjoyment, that's what's happening. Level A, level B. And once again, I think we've seen this enough. We have enough flavors here and color spaces. Makes NTSC look so appealing. Optical interfaces. Because we've reached the limit of what copper, our good old friend, can do. So we need to move on to the world of fiber. Because it makes sense. You start doing 10 gigabits per second, you're not going to put that through a piece of coax. That'd be 30 gigabits of frequency response to get a square wave. You might be able to do that over 3 feet, but what's the sense of having a 3-foot piece of copper? It's not buying you anything. Go to optical. So there's some standards there. You want to pull those out if you're getting into the world of fiber and do some fancy reading. Virtually unlimited bandwidth. Once you put the get rid of the copper, put in the optical, you change interfaces on both ends and you can future-proof yourself until you retire. Support higher frame rates because it's optical. You just keep jamming in more and the optical says thank you very much, where copper says I'm had enough. High performance over long distance because you can go many, many kilometers with optical. Telco companies do it all the time. Cable companies do it. You can go 60 kilometers, no problem. Reduce sensitivity to electrical interference. You don't have to worry about going next to a 13,000 volt transformer on a line somewhere. It's glass. It's not affected by any leakage. Smaller, lighter trunking, well, it depends. Fiber optic is cheaper than coax. It depends. Depends on what the interface costs on both ends. That's always the trade-off. Am I gaining or losing? I get rid of all this copper, put in optical. Do I have more sophisticated interfaces on both ends that consume more power, produce more heat, and weigh more? I work with people who do trucks, and they're always up against the absolute maximum weight they can have in a truck. And if they add one more thing, it's like, we got to take something out. So that's constantly, depends on your business. I work with people that do airborne platforms. Every ounce is too much. So they're looking at how do I get rid of this and add that, and do I really gain at the end of the day? Optical basics. We put a square wave in. We have copper in the old days. We have glass now in between. And we have a detector and an amplifier on the other end. Just basically taking the electrical and moving it to flashing LEDs or lasers. You get what you pay for. And there's the cladding. It's all about, like anything else, it's about the quality. The quality of the glass, the cladding, how robust it is, how the protective coating, is it going to survive all the things you can do. I'm still amazed you can bend glass, but it works quite nicely. The cladding keeps the light inside the core for reflective index because you have your piece of glass and reflective sheathing keeps the light inside the optical, or else it just leaks out like anything else. It just lights up the world, which is not the purpose of what you're doing. You see different frequencies of light, the attenuation curves, your absorption of water, and infrared absorption for your reference. If you move into the world of optical, you can have maximum power. You can put as much power as you want to. I mean, as long as somebody doesn't stare into the end of it, you can get ridiculous with the amount of power. You can burn somebody's eyes out if you're not careful. I had to go through that training at IBM. They used to show us pictures of burning rabbits' eyeballs with lasers. Like, that made a point. But so we didn't burn our eyeballs, so we're working around high-power lasers. Polarization. You start going through a medium, you can actually flip the polarization as you're going through the glass. Does that matter? Depends on what system you're running. You have cable loss at your joints, your insertion loss. You follow the SMPTE specs on all this. So there we go. We put a nice square wave in. We have a long fiber run. What comes out the other end? Look at that. Just like copper. You start losing the high frequency. It's the laws of physics. Whether it's the air, the ocean, copper, or glass, high frequency gets lost. Square wave into a sine wave. Just we can do it at a whole lot higher bit rate, but the laws of physics, unfortunately, still apply. Spreading of light during transmission. The laws of physics still apply. You have a square wave that is actually rather rich with frequency content. That's what makes it a square wave. It has a lot of frequency information. And the laws of physics, you put a complex signal through something, you have group delay. The frequency doesn't come out as exactly as it went in, so you start having rounding and squaring of the waves. Complex signals in the world of electronics, high frequency and low frequency don't come out the other end at the same time, so it starts spreading, you start having a sine wave. Multi-mode, you have different wavelengths of light, not the same quality of glass, so you have more loss. If you're going 100 kilometers, you want to use single mode. Multi-mode, people are getting away from because the cost of single mode is going down. Multi-mode is good within a facility. So we have more connectors to worry about, if we didn't have enough already. So you can have that for your reference. How do you join the optical together? You have an air gap. Well, how much loss can you take? Because when you're doing fiber infrastructure, you have a loss budget. Between here and there, the glass itself gives me so much loss. I start having splices, backhoe, fade, or whatever you're dealing with. You're not going to get what you put in to begin with. So your splices are very critical. So training as far as splicing, the cleanliness, the shaping of it. As you can see, the more complex you get with the 8-degree angle, because the reflected light, when it hits the change in impedance, is actually reflected somehow back into the optical. SFP, we have pluggable small form factor for putting it into a back of a unit. So whatever type of fiber you're using, whatever frequency, it's plug and play, hopefully. Talk about your budget, your receiver sensitivity, it's laws of physics. How much am I putting in, how much am I losing, and what sensitivity do I need at the other end? See your splicing budget, how you have losses, your margin. You want to make sure at the end of the day, because the fibers might be in there for another 10 years, 20 years, who knows how long, it's going to get splices. Things happen. People dig up stuff by mistake. Happens all the time, and you got to go in and fix it. So how much margin do you have before it's all over? HDMI, just what we need, another interface. This is I work with audio-video people that are doing sports bars, hotel lobbies, all that kind of stuff, and HDMI is driving them crazy. The HDMI is a problem, which the HDCP, the encryption is really the big problem. We have a new device called WFM5250 that has SDI and HDMI. And I have learned the ways of HDCP by doing the training. You don't want to mess with the people that spec out HDCP. They're ruthless. If you want to do business with them, consider it your honor, your privilege to have the moment to work with them. Anything you do wrong, they're finished with you. If you have any equipment that looks to them like you're trying to beat their encryption, they're finished. Sorry, we're done. We don't trust you. If you have equipment that doesn't meet their standards, they just say, sorry, you're no longer part of this. Because they are protecting the kingdom, the content. Content is king. If you can figure out a way to break HDCP, you can do very high quality copying of very sensitive, expensive content. And believe me, that is something they do not want you to do. I mean, the training we went through and all the problems of dealing with HDCP, it's like taking a course in law. That's what it is. Okay, so there's different flavors. For 1.4 is the latest for your reference. Kind of a neat concept here because you hook up an HDMI piece of content. You want a hot pluggable detect. How does it know something is there to start all this questioning and answering and handshaking? There's usually something that says, wake up, I just connected something. So you have your detect, your high and your low, you break the connection, it stops putting out the content. You start getting in the world of HDCP, the encryption, hot plug detect wakes up the handshaking. The handshaking says, I know who you are. You're not a recording device. You're a display device. Here you go. Here's the content. But I don't trust you. I'm going to test every 10 seconds to see if it's still you. And if it's not, shuts it off. And that's it. So a lot of compatibility issues. People in the AV world, which might be what you're doing, HDMI with HDCP is a challenge. Customers like stuff to work. And you can put in your 4K, all that versions. This is for your reference. As far as the horizontal and vertical sync, it's still time. But HDMI has another layer of protocol because you still have sync, you have header information, you have active video. It's the same thing, just packaged a little bit different on a different interface. For your reference there, you can talk to all your friends about the packet types. Aux data status, that's great. We can look at the color and all the information of HDMI with SDI, HDMI. But what if things aren't working right? I need status screens. I need intensive care ward, medical screens asking the right questions. to hopefully get the right answer back. So we have status screens for HDMI, and all your packet timing, your interface clock information is there. EDID, Extended Display Identification data. What this is so the source, the sink provides the EDID to the source. The sink is the display. If it's not a display, if it's HDMI with HDCP, it's going to say, I don't know you. But let's say it's a display, which is what it should be, coming out of a set-top box or whatever it is you're doing. The source, the display, says, wake up. No, the sink is the display. Says to the source, wake up, I'm here. And it says, okay, I see you, but tell me what you are so I know what to send. And it looks at all the manufacturing date, the serial number, all your chroma specs, what standard it is, and says, okay, I can deal with that, and it sends the content to the display. If it can't handle what it can handle, it says, well, I'll give you something less, downwards compatible. So at least you see something, if you're lucky. So I can see what's coming in and what's going out as far as the EDID. If our device is in the middle, it needs to be talking both ways, so the source and the display on the other side know what's going on. Hot plug detect, that's an important thing. HDCP, as I haven't scared you already, it's a pretty ruthless crowd. They don't play around. Video over IP interfaces. I think we'll have a break coming up here. No, you gotta wait for a break. Maybe we'll have one early. It's a long drag. Is the temperature okay in here? Is it too warm? Sylvia! Somebody out there, it's too warm in here.
Are you guys sweltering?
Yes.
Or if I stand up and start fanning?
No, don't.
I had the fellow in earlier, so
So anyway, if you could contact someone to get some cold air piped in here, we'd all appreciate it. So anyway, if you need to get up at any time, feel free, but I need to keep going. Okay, video over IP. No big deal in the world of compression, so that's my part 1, part 2, part 3, and all that. 5 and 6 is pretty much what we're going to focus on. This is high bitrate media signals over IP, which is intended to be uncompressed over IP. As I said, I did the SMPTE seminar series in June, did Toronto, Montreal, Hartford, Connecticut, and where else did I do? DC. So anyway, we did all those, and what I learned, uncompressed video over IP sounds great. It's not happening for a while. Is there a business case? Not yet. Is it too expensive? Yes. Does copper seem to work so far? Yes. But in the world of going to over-the-top TV anywhere, eventually you put it into an IP structure and it just goes off into the rest of the world. Whatever you need to do with it, transcode it, scale it, whatever, it's already in an IP packet, so off it goes. But it's expensive at this point. So SDI needs to maintain data integrity. That's nice because in IP, it might. Because IP is packet-based. And that's usually where things fall apart. You can have gross reordering of packets. And in SDI, it can't happen. There's no, okay, resend it, let's try again. It's live television. There is no time to do that. You have burst losses and drops, so we'll talk about forward error correction. What is forward error correction? It's like bubble wrap. If I'm going to put this laser pointer and drop it off at the post office and mail it to my house in Virginia, do I just walk in and say, here you go, send this to my house, and never see it again? Well, I probably never see it again. What you want to do is wrap it in bubble wrap. Protect it. Do I need more bubble wrap at my home? I got enough bubble wrap at home. I want to make sure this makes it to my home. So forward error correction is extra ones and zeros you put in to your content, realizing all of it is not going to make it. So it's an overhead budget of extra ones and zeros that if you lose a certain percent, it has recoverability. Because forward error correction, I used to have a section on this, but it got kind of cut to nothing. Forward error correction, if a 1 or a 0 is, you can't determine a 1 or a 0, or a high or a low. It goes to a lookup table for forward error correction and says, well, was this supposed to be a high or a low or a 1 or a 0? It goes to the lookup table and says, oh, by the way, here's the missing data for my calculations of forward error correction. Go off and do your work. But it's like bubble wrap. You start popping all the bubbles, eventually you don't have any more bubbles left. It's the same thing with forward error correction. You only have so much. You only be putting 75% of your payload as forward error correction. That's kind of silly. So there's a trade-off of how much is enough and how much is ridiculous. SDI plant, well, that looks pretty simple by today's standards. Good IP. If you put on your magic glasses, that's how simple our future could be. Look at that. Isn't that nice? I was at a lab facility in New Jersey where they actually invented the transistor many years ago. This was a facility that used to have 5,000 people working in it. Now there's grass growing through the parking lot cracks. There's 100 people in this building. And it was, the survivors were PhDs, research people that were coming up with a wireless infrastructure. You wouldn't need cabling between anything. You plug it in, it talks to itself, and the signal just moves from point A to point B. Wouldn't that be wonderful? Well, they all got fired, so that was the end of that. Too good of an idea. So we'll go back. Now, this looks like more fun, doesn't it? We'll have all that. A wireless video facility. Everything just talks with Bluetooth, whatever protocol they were working on. But until then, until they start their own company or whatever they're going to do, we're stuck with that. Okay, so IP packets, SMPTE 2022. That's the spec I would recommend if you're moving into this, but don't rush too fast into the world. And there's IEEE. There's no compression, optical, forward error correction. So low latency is what we're looking at. So I think really the whole idea of broadcast, real-time, uncompressed, IEEE is the way it's going to go. You need the gen lock. As we talked about in the beginning of today, when you're doing real video live, you're taking feeds from all over the planet. They've got to be time accurate. Video over IP in the classic sense, you're compressing it and sending it out over IP. It's a finished production. Our business is creating content. Well, if you're creating content, you need time accurate to the pixel, timing. So if you're creating content, that's what you got to do. All right, who's next? Let's see, we're in 8. What time is it? We're taking a, can we take a 15-minute break? I know it's a long